Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Chen with us today. Hello, Ken.
Hi, Frank. It's nice to have the chance to speak here.
Well, it's a very awesome article we're going to get to here in a shortly. Yeah. And Ken, what is your geolocation? Where are you at?
Now I'm in the Heidelberg, Germany. The weather
Heidelberg.
is pretty nice at the
Oh,
moment. Yeah.
lovely. So it is August 25th of 2025 as we record this, and I'm in Phoenix, and we are definitely in our summer mode in the Sonoran Desert, which is actually the wet season. So we're probably going to get some rain here over the next couple of days, and that'll be very nice. Help cool things down a little bit as we go through. So good.
Yes.
Very nice.
Mm.
Let's see. And Ken, what do you like to do for research?
My research interest in mainly on the computational and theoretical astrophysics,
Hmm.
and I might actually spend a lot of time doing the supernova explosion. So probably at that time knows about Frank because you all used to be the editor for this astrophysics.
Just look
And
at you.
also the later I will be switch a gear to a little bit interesting on the more larger scale and more early universe, the cosmology and the formation of the first stars and the first galaxy.
Very
That's
cool.
the work here actually has been developed or been thinking of forced for a while to eventually come out at this year. Yeah.
Very cool. Very cool. Well, I like the range of spatial scales you cover from stars out to a little bit larger, let's say. So very cool. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Formation of supersonic turbulence in the primordial star-forming cloud. And Ken, take us away.
Yes. Okay. So this work is just recently published in the later, and my co-author actually they are my students. The
Mm,
first one is Mong Yuan Ho, and she is my research assistant at the ASIA, and also the Pei Chen Dong. She is also the research assistant with me at the ASIA.
great
Yeah.
shout out. Great shout out. Good. Okay, let's go ahead and let's get into it.
And here, there's the article, the story about this article is about the formation about the supersonic turbines. Originally, actually, this is just like a conjecture. This is like a just purely suspect whether really the supersonic turbines can form or in the universe. And
Mhm.
the story comes with the importance about the turbines because turbines are very important physical process in the many astrophysical process, like a star formation, like a accretion disk, like a
Mhm.
interstellar medium, giant molecular cloud, and so on. So the question come with us is about whether during the first star form is any turbulence. If yes, what's the property of these turbines?
Okay.
So they bring out this kind of idea I want to search about to understand the nature of the turbines during the first star formations.
I'm with you.
So the idea then we want to do this from the first principle. So we try to do this from the cosmological initial condition and try to simulate the formation of the first stars from very large to small scale.
Cool.
And this first star usually called the top three stars,
Yes.
we know. And so what's interesting and unique about this later is
Okay.
because there are actually many of the first star simulations, and some of them also very high resolution.
Mhm.
But the key of this, the novelty and the breakthrough of this work is we try to simulate from cosmological simulation to the formation of the mini halo to lead to the formation of gravitational driven turbulence in the mini halo, then lead to close to the first star formation clumps.
Cool. Hmm.
So it's huge. I mean, this is not easy to do. So we try to take advantage of the cutting edge simulation initial condition, for example, from the TNG simulations,
Uh-huh.
and also using a method called the particle splitting. So we further refine the simulation from this electric TNG simulation by 10 to 5
Ooh, nice.
so
Okay.
10 to 5, much higher resolution in the particle mass
You need it.
to resolve the turbulence.
Hmm. Very
Yeah,
cool.
so that's why we will be able to really simulate the formation of the turbulence. The previous work, they have high resolution. However, their high resolution simulation only focus on a very small narrow region, which is the first star formation.
Hmm.
However, due to this kind of very so-called hierarchical AMR simulation,
Hmm.
they focus very small region of the very highest resolution. They smeared out most of this kind of turbulence development.
Yeah.
So in this jumping between different level of the grids or particles, those are actual turbulence has been sort of like a smoothed out.
Figured out. Yeah. Yeah.
So you won't be actually to see the real turbulence formation inside previous first star simulation.
Okay.
So on the other hand, we try to make our best and simulate with a uniform highest resolution to simulate this turbulence formation. So we will be able to catch up the turbulence cascade
Yes.
from this halo scale
Yes.
to the star forming scale.
I'm with you.
So
Hmm.
that's the idea and the method we try to do with this paper.
Very cool. Very nice. Hmm. Good.
So, and the other things is very our surprise. Maybe we can go to the figure one.
Yeah, sure. Well, let's say a little something about the tools we're using here.
Yeah. Oh, the code here. Actually, we use the Gizmo code. So H Gizmo code is like it's a very nice code developed by Phil Hawkins. It's very
Yes.
good code.
Yes.
And the unique thing is it's like using this kind of mesh free method. So it's like a particle, but it's also have a some kind of better resolution on this capture the shock wave and the discontinuity, which is very important in this turbulence simulation, especially a supersonic turbulence part. And we also use some of these chemical reaction network, and this actually some of very comprehensive chemical reaction network with a Greco package
Yes.
and putting about 12 species and try to model the primordial gas cooling and chemistry coupled with hydro and unbody gravity sort of cell consistently.
Good.
Yeah, this is our method. Yeah,
Good. Always good to give the software instruments a shout out. So yay to
yeah.
Gizmo, yay to Grackle. Okay, so now we got our tools and initial conditions. Okay.
So the initial condition is using the TNG simulation, so which is actually a state of art of cosmological simulation, also with a magnetic field. And then we use the TNG 50, which is the highest TNG series of the simulation. And although this resolution and is very high, and we use this kind of public kind of sort of the directory, we can available the hello information available download for the other people, and then we get out these halos and try to find one of these so-called mini halos
Huh?
before the mini halo formation. So the candidate of these mini halos, and we follow the evolution of that halo to form the first mini halo,
Gotcha.
which later then the first star will be actually formed inside these halos in the TNG from the TNG initial condition.
Cool. Okay. Cool. Okay. Yeah, let's see.
So, however, I want to say something about after using this initial condition, however, the originally TNG resolution
Ah,
is not good enough. It's like originally for the gas and dark matter particle is like 10 to 5, 10 to 4 solar mass,
right, right.
which is too
Too coarse.
crude for
Yeah.
the simulation for any turbulence formation. So our approach is we try to splitting the particle. We try to cutting the original TNG particle into small particles. But we don't have, we can actually, we cannot cut all these particles, a very small particle at once. The reason because we try
Ah,
to do is gradually. This is a trick. So we need to cut one, for example, divided by two,
yes.
and we evolve the structure. It'll be, then we cut in gradually.
Yes.
And we were getting smooth evolution.
Cool. Yeah.
And when this, especially dark matter particle, start to form these halo structures, then we gradually reach our optimized resolution.
Okay.
We turn on the physics, gas physics, chemistry, cooling, blah, blah, blah. We turn on this physics, then we evolve the entire
Mhm.
system until we finally form this so-called mini halo in the
Cool.
forming gas.
Mm-hmm. Yeah,
Yes,
great resolution there. Mm-hmm.
yes.
Really nice. Mm-hmm. Cool. Okay.
Um,
And how long do we run these for? We run this for this much
it,
time. Okay.
yeah, so actually this simulation because the resolution is really high and eventually the resolution will be killed by due to the small time step. The reason because we don't put any thin particle. Actually, in this simulation,
Okay.
we focus on the cloud and the crown property. So we don't put the thin particle to mimic the star formation. So that leads to, at the end, some of dense region, which is already subject to collapse of the cloud,
Yes. Which is what.
time state become extremely small. It's so small, the coolant time state is so small, then eventually you killed the simulations.
Mm-hmm.
However, we already get our signs out before the simulation
Right.
uh, being terminated. So
Right. That's
we
great.
run this simulation actually from redshift about 20 to 18-ish.
Yeah.
So the physical time like 17 million years.
Uh-huh.
In terms of star formation, time scale is actually still much longer, but we just want to simulate from the pre-mini halo to mini halo and star forming cloud formation.
Yes.
And after about 500,000 years after kill the simulation, it probably will evolve to the stars.
Mm-hmm. Mm-hmm.
Traveling
That
the,
started. Yep. Very
so
cool.
that's the process of the doing these simulations.
Cool. Very nice. Thank you. Okay, let's go ahead and get into some of the results. What do we get? Figure
Yeah,
one.
so maybe start from the figure one. So you can see this evolution, this time progression of this evolution of the far cosmological star formations, star forming cloud simulation. You can see originally the density structure in the universe you see some little bit kind of pattern, but not very clear. But because initially the gravitational potential wave from dark matter halo still like from just evolving, start growing.
Mm-hmm.
And after soon from this redshift, shifting a little redshift by zero point 0.4 something, you can see the dark matter structure start forming, and then you can see there's the white this air the string lines
Okay.
represent the velocity of
Yes.
the gas.
Yes.
So
Yes.
the velocity seems to move into one of some kind of singularity point. So actually, it's a convergent flows.
Yes.
So those indicate the gas start to inflowing into this converging form, which is actually a gravitational potential formed by this from the mini halos.
Yes.
So after a little bit more time of the evolution at the final snapshot, you will see the gas converging and form a concrete, a clumpy gas. And you can see some kind of spiral of the gas
Oh,
in
yes. Uh-huh.
this, inside the cloud. That represent actually the cloud itself actually being formed, and the cloud is not quietly. It's like some chaotic motion, such motion
Yes.
happening inside this cloud.
Very
Yeah,
nice. Good. And people wondering, this is number density plotted.
yeah, this number density.
Uh-huh.
Yes,
Cool. Okay.
and probably can go to this the next figure.
Sure. Okay. Slide on down. We're getting into the properties of the turbulence here. And here we go. This is a big figure, so I'm going to zoom in a bit so we get the whole thing, and we'll zoom out as need be. Okay.
Yeah, so actually this figure is showed at the final snapshot. What is the density structure zooming into the halo? So we go from like a more like a semi-cosmological scale, 40 kiloparsec scale, going to 440 and 4 parsec scale. So
I'm with you.
if you look at this, like the size of the mini halo, the mirror radius roughly is on the 400 parsec panel. If you look at these panels,
Uh-huh.
and you can see inside the center of this halo, you will see a clumpy, not the irregular turbulence
Right.
like structures.
Mm-hmm.
It is to show the density. It's now to show the density. So we just zoom in to see what happened inside this block of the gas.
Very
And
nice.
you see some filaments, some small clumps on this third 40 parsecs panel.
Nice.
And you see some of the very more dense region, like some bright spots dot at the very center.
Yes.
And then we continue zooming 4 parsec scale. Actually, there are actually more stuff inside this pole, the very bright spot.
Yes.
Inside. Later, we will zoom in at the final, but let's go continuous to maybe to figures 3. So because we want to understand what's the physics for this dark matter and the mini halo and these clowns.
Okay.
So
Great.
we try to plot some of the physical quantity we want to get understanding. So we plot the density, the blue, bright colors. We
Mm-hmm.
plot the dark matter particle distribution. We plot the temperature and also the Mach numbers
Ah, okay.
of these halos.
Uh-huh.
And you can actually tell something very interesting here. So actually the density distribution actually match well with dark matter distribution.
It should.
The reason actually because dark matter actually it dominated the matter budget and it provide the gravitational potential well
Mm-hmm.
which will forge allow the gas like a ball support the ball and the water the barrel can hold on the on the ball, then you can form the stars. But interesting things here, you look at the temperatures here.
Mm-hmm. Okay.
So the temperature, you can see the reddish color is more high temperature, the green, the blue color,
Yes.
lower temperature. But actually, the higher density region have a lower temperature. The reason because here is because at the moment the molecular hydrogen start to form. And the formation of molecular hydrogen actually serve as a coolant
Yes.
to cool the gas is very key. So key to for the star formation. If you want to a star to form, you need to cool the gas and the gas condensate to form the stars.
Yep. Cool.
And we now know, okay, that is very central region. You see actually the blue and the red, blue and greenish colors. This
Mm-hmm.
is the formation of the star formation region. And
Yes.
you see, and actually on the Mach number panel, actually you see the entire cloud itself. I mean, you see the white dash circles.
Uh-huh.
White
Mm-hmm.
dash circles means 100 parsecs
Mm-hmm.
of
Okay. Yes.
no, sorry, it's a virial radius. It's a virial radius of the mini halos.
I'm with you.
So actually, you see the halos itself actually is full with supersonic turbulence flow.
Mach
So
number.
the Mach number of this flow
Mm,
actually is supersonic because Mach number is larger than one, and actually the sort of like a in average or characteristic Mach number of the halo actually in this case is about five Mach,
okay.
about five.
Okay.
So this kind of supersonic turbulence flow is unlike the normal subsonic flow because the supersonic flow he can compress the gas,
Yes.
he can fragment the gas, he can
Easily.
disrupt the
Mm,
homogeneous of the gas
cool.
and create the fragmentation and filaments.
Good.
That's very important because in previous simulation, actually these kind of things actually haven't been actually discussed
Cool.
or be observed because the thing is that if you cannot resolve this flow pattern, you cannot say anything on
Good
this.
evening. Yeah.
So this is actually the first time is like we can able to resolve the. I also call this kind of first turbulence, maybe the first turbulence of the universe.
I love
So
that. That's great. That's great.
before the first star formation. So this actually is still consistent. And this turbulence is also unlike the turbulence we see at the present universe, because in the present universe, yes, there are some gravitational driven turbulence, but we also have other things. It's like the like a supernova driven or the radiation bubble, all other different things to driven the turbines. But in the early universe, in the first stars,
There isn't that.
only we have nothing. We only have gravity, but the gravity is strong, is good enough to driven very decent supersonic turbines. Also for the first stars case.
Beautiful. Beautiful.
So
Very
then we can probably get to more understand about the turbines and we can go to the figure 4.
figure three, figure four, power spectrum.
Those are the more like a quantitative understanding the figure. So you can see this is
Yep.
so-called power spectrum of the fluids. So and then we try to plot this usually so-called the Kolmogorov spectrum. So we drawing the power spectrum in terms of scale and how it evolved with the scale. We see there's a power law decay. This indicate this turbulence of the Maxwell's Kolmogorov spectrum K to the minus 5/3.
Yeah.
And the next figure you can tell is the property of this turbulence. So we plot the Mach number of the gas in terms of their mass fraction.
Hmm.
So actually, the highest Mach number, probably 25, maybe something
Wow.
close 30-ish,
Wow.
is really, really high, but it is only occupied very small fraction. So if you see the peak of the distribution, roughly about 5, Mach number is about 5.
Yeah. Hmm.
Yeah, so this is a kind of like a log normal, like a distribution to get understanding the distribution of the turbulence. And maybe go to the figure 6. And
Cool.
figure 6 is the phase diagram. So we
Nice.
want to understand about the sort of the gas property, gas physics, thermodynamics for the first star formation region.
Right.
And we try to draw the density and the temperature. And you can see very interesting thing, just like I suggest that that's just show. When the density goes to higher and higher, actually temperature getting lower and lower. These are due to the interest in these molecular hydrogen
Totally.
formations.
Yes.
the cooling of this tail. So actually at the end, the tail, the high density tail part will eventually lead to formation of the first stars.
Notice temperature is about 100 people.
Yes, so this is actually the gas there will be star forming gas.
Uh-huh. Very cool.
So maybe let's go to a little bit to the figure, next figure,
Cool.
figure
Thermo.
seven.
Go from thermo to a volume render here. Okay.
So this is a kind of candy figure or was is showing the 3D volume rendering of this at the very center of this the
Hmm.
bright spot I showed in the early figures. So inside this bright spot actually has structures. So you can see the special pay attention to this red
Yes.
and yellowish
Yes.
like a nugget
There.
and a
Yep.
nugget. Those are actually the core, the dense core of the cloud.
Yes.
And this dense core actually will be the parents cloud for the star formation. And we know there's a very good correlation between the core mass and the star stellar mass.
Yes.
There is some good correlation. So actually here we show there's multiple dense core forming in a very small region. That's, that suggests the first star, even at the cloud level, it already start to fragment
Yes.
due to the supersonic turbulence,
Okay.
which actually no one actually discussed in this in detail. Because the pop 3 star formation community usually discuss the fragmentation is during the
Okay.
disk fragmentation,
Yes.
but the D is earlier than the
Yes.
disk.
What is
So
what is the rough masses of those red?
this is the one of the I show one of these the bounded the cloud is about a solar mass.
Okay. Not
So
not 150 or 200.
no, not at all, not at all,
Okay.
no.
That's important.
So so during this cloud for fragmentation by the supersonic turbine,
Hmm.
is actually we have been actually lower the the mass scale of pop 3 star from several hundred, even thousand solar mass
Yes.
down to 10, 10th-ish solar mass. This already, and later probably the disk also will fragment. So that's not unsure. It's still not 100% guaranteed. But anyway, the cloud mass, the dense core mass is actually can easily correlate and set up upper limit for the star at
Yes.
the form inside the core.
Ooh, right. Yes. Yes, yes, yes. I'm with you. Hmm. Yeah.
So in this very kind of important because the thing is when you think about the first star, pop 3 star, they are 100 or 200 solar mass,
That's the
and
story.
they will die so-called appearing stability supernova. And the creature I have spent a lot of PhD time simulate this kind of very massive star, first stars.
Yes, you did.
And however, the observationally, it's difficult to convince or to prove about the existence of this kind of massive star
Yes.
for Pantry star. They might be still exist, but maybe the number will be much lower than we think because from this simulation having suggest. So, and also from the observational part, people observe so-called metal star, the
Yes.
EMP star,
Yes.
and then we think about they are formed right after the first supernova explosion.
Hmm.
The good match of this abundance pattern from the first supernova actually suggests not the parent stability supernova. It's more like a core collapse supernova and also some of the hypernova case. So there's actually some discrepancies.
Yes.
And this kind of simulation actually further support the idea probably the pop 3 star may be not as massive as we think to be.
Okay. Okay.
So that's a kind of point of we want to make in the in these papers. And actually we also been working on others. Actually, there's another paper actually being submitted. We are revising also to ABJ. So we simulate like a 20 of each of the mini halos and
Okay.
want to get a good, nice statistical property of the turbulence property of these mini halos and the way the is any correlation with the mass or the property of the mini halos and try to further make sure about the existence of a supersonic turbulence. And the other interesting thing to doing is the magnetic field. So me
Yes.
thinking, so putting the magnetic field
Yeah.
effect to see whether any small dynamo, the small dynamo effect
Uh-huh.
play important role in shaping this first star forming cloud and
Hmm.
also the mass of the first stars from
Mm.
this simulation. So
Very
basically, this the the work we are trying to present, and hopefully we will make sure try to get more understanding about the physics of the first stars, the genesis of the universe, and the cosmic dawn, and those.
very cool. Beautiful work. Beautiful work,
Thank you
Ken.
very much.
Yeah. Very nice. Yep, yep, yep. Okay, Ken, thank you so much for walking us through your very awesome article. Very
Thank you
nice.
very much.
And you touched on it a little bit there at the end. And so let me go ahead and push on it and ask, where do you think we go from here, given the published article? So you mentioned, yeah, one might be concerned about MHD effects in
Mm.
those small clouds. Uh, could there be any evidence? Do you see any? Is it a potential direction? Do you see binaries or multiple star systems as you get on down there? And
Mm.
just sort of next steps, where do you think we go from here, given the published article?
I think the key important hints about is try to give a signal to also to the top three or first star community.
Yes.
So the thing is we want to actually we should very careful about the turbulence and be careful because in numerically this high resolution simulation can really achieve in the first star community, but usually this kind of trade-off about the turbulence because you just put all the simulation resolution on the very small star region.
Right.
But so I think the next step for the community, I think we should also try to make an optimized way. Maybe we need to have a better resolution at the halo scale,
Okay.
allow allow the turbulence cascade can be simulated and evolve down to the star forming scale.
Hmm.
That will be also the interesting idea of these things to
Yeah.
do. And also try to get more detail. For example, here, the simulation here, I didn't go into further after the dense core collapse into the star. The
Uh-huh.
next step will be also interesting to see how this dense core eventually evolve.
Yes.
Not only about the star, maybe they will form the binaries, but maybe they also have some interesting thing, whether not so sure whether it will continue fragmentation
Yes.
or it
Yes.
will have other anything unusual. So this moment we didn't deep into the star formation because this
Uh-huh.
complicated, more
Uh,
complicated. Depend on how you treat the thin particle, how do you do the star formation, very
correct.
numerical.
Correct.
And other things we think about is observationally because now we have the JWST. So we are actually looking into very high Z galaxies.
Hmm.
Maybe it will not be easy to see the first star, but the first star plays really important role. So that's why the mass scale actually affect now the radiation output, the supernova explosion, nuclear synthesis yield. They
Hmm.
eventually will influence the first galaxies. So the thing is, we actually also have some work with other collaborators try to study the follow-up, some of the follow evolution
Cool.
to understanding from the first star to supernova to the galaxies.
Yes. Yes.
So hopefully that will be produce some kind of self-consistent work to get understanding about this high G galaxy observed by the JWST. This is kind of a very big campaign and people are
Uh-huh.
involving in the working toward the direction. Yeah.
Very cool. Well, it's going to be really exciting over the next couple of years between sort of the new simulation avenues that you've opened up here with this article and the capabilities of JWST and clustering, gravitational lenses, picking up far distant objects. Be very interesting development over the next couple of years. I'm very excited about it.
Yeah.
Cool.
Thank you
Ken,
very
thank
much.
you so much for walking us through your article again.
Thanks so much, Frank, for the invitation to
Sure.
share.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.